For this lab, we're going to deal with thin layer chromatography, and we're going to do thin layer chromatography on the aspirin sample that we've synthesized. So let's talk about what thin layer chromatography is. It's a type of chromatography. Chromatography is a separation method used in chemistry to separate mixtures of compounds. Depending on the type of compound, that's going to determine what type of chromatography is used. Thin layer chromatography uses a silica gel plate, which I'll show you in a minute, as the stationary phase, and some type of solvent as the mobile phase. And so I'll show you how that works in a minute. So the stationary phase is just what it says. It's the phase that does not move, and normally it's some type of adsorbent particle. In this case is silica gel. You know, adsorb means that something is on the surface, where absorb means that something is taken in to a particular type of particle. So in this case, we're going to use silica gel as our stationary phase, and in the mobile phase, we're going to use a solvent system made up of hexanes and ethyl acetate, which I'll tell you about in a minute. TLC will allow us to see a couple of things. Number one, it'll tell us how many components are in a mixture. If I spot a mixture on a TLC plate and I get 5 spots, then what that means is that that particular mixture has 5 components within it. The RF value, we're going to talk about that. That's just the distance that the spot travels versus the distance that the solvent travels, and I'll show you how to calculate that in a few slides. So silica gel coated plates, that's what this picture is. It's just white plate, white either glass or plastic or aluminum back plates with silica gel on the surface. Okay, and to illustrate how silica gel works, here's silica gel. Here is just a network of silicon oxygen bonds with hydroxyl groups coming off of silicon. And the way silica gel works is it works based on polarity. So really polar compounds stick to the silica gel because of the OH groups. They find polar functional groups in polar compounds and they stick, whereas compounds that are not so polar don't stick as well and they move much faster. So let's look here. All right, the blue, you can see the blue dot move pretty quick, and then the red dot is just kind of chugging along, and that's because it's sticking to the silica gel better. Let's do that again. So here's the blue dot. It goes quickly across the silica gel. What that means is that it's not very polar. The faster a compound moves, the less polar it is, or the less polar we can say it is. And then with the red dot, you see again it's moving very slowly, and that means that it's attracted to silica gel, and so it sticks to the surface and it doesn't move as fast. All right, so how do you prepare a TLC plate? First, you need to cut a 2x3 TLC plate. I'm going to have these ready on tomorrow. We'll cut them. They're plastic back plates. One thing to remember is to not touch the surface with your fingers, so you need to wear gloves when you're handling the TLC plates. All right, so you cut your plate. What you're going to do is draw a line and pencil across the bottom of the plate, and then you're going to mark just above the line where you want to spot your compound. Next thing you want to do over here is to add a little bit of your compound to a test tube and dissolve it up in a solvent, and then you take a capillary tube and you dip that capillary tube down into your solvent, and that capillary tube, now we want to take the solution that's in the capillary tube and come here and put that onto the plate. So you want to gently tap the end of the capillary tube on your spot. So you'll do it once, and in between taps you want to blow on that spot to evaporate the solvent. So you do it twice, and then you'll do it again until you have all of the solution that was in the tube, in the capillary, is now here on this spot. And again, as you tap, in between taps, you want to blow that spot to evaporate off that solvent and make that spot, you want it to be as small as possible. Really big spots tend to streak up the plate. Really concentrated spots tend to streak up the plate, so you don't want to have a huge, really concentrated spot. So you want a really small spot. And again, as you tap it, you want to blow. Every time you tap, you'll see the solvent go onto the plate. You blow on that to evaporate that solvent. Alright, so the next step is to prepare what we call a developing chamber. It's a fancy terminology. All it is a watch glass and a beaker. And so you want to put your solvent here. This is going to be your mobile phase. The solvent, capillary action of the solvent will move your compounds up. And so here for the TLC of aspirin, we're going to use 60 to 40 hexanes ethyl acetate. So you want to place your TLC plate into the developing chamber with the solvent. In this case, it's going to be 60-40 hexanes ethyl acetate. That'll be pre-mixed before you come. And so what happens is, again, the solvent vapors, the capillary action of those vapors are going to move your spot up the plate. Let's watch that again. So you see one spot is moving a lot faster than the other one. Once again, that because of the polarity of the spot, if it's really polar, it's going to stick well to the plate. It's not going to move as far. If it's not very polar, it'll move quickly up the plate. Let's watch it again. You see the spot here on the left side moves quickly, and this spot moves pretty slowly. And what that means is that this spot is not as polar as this one. So this one has more of an attraction to the silica gel that the plate is coated with. Alright, so the next step in the progression is to do what we call visualization. That can be by UV, which you see here. You'll put your plate under a UV lamp. If there are any pi bonds present in your molecule, they'll show up under UV. And so you can use UV visualization. And what you want to do here is every spot that you see, you want to circle it, because we're going to have to measure the RF at a later time during the lab. So after UV visualization, you can also use some type of stain. In our case, we're not going to use a stain, but if you do use a stain, the proper procedure is to do UV first and then stain. You never stain first and then do UV. So different types of stains are PMA, which stands for phospholipid acid. Vanillin is also a stain, and potassium permanganate. All of these stains are specific for certain functional groups. So depending on what functional groups are present in your compound, you can use a stain to kind of pull that compound out and show that it's actually present. So that's what visualization does. It lets us see each spot on the TLC plate and where that spot is relative to the line that you started at. Alright, the last thing you want to do for TLC is calculate what's called the RF, or the retardation factor. What you want to do is after developing your plate, you want to stop that, take the plate out when the solvent gets about 1 centimeter from the top, and then you can measure from the line to your spot, and that'll tell you the distance that your spot traveled. And you can also measure from the line to the line where the solvent stopped, and that'll tell you the distance that your solvent traveled. That's called the solvent front. If you divide the distance the spot traveled by the distance that the solvent travels, that gives you what's called the RF, or the retardation factor. And this number is going to be larger for less polar compounds. It's going to be smaller for more polar compounds. So what are you doing tomorrow? When you come, you're going to prepare 3 test tubes, one with synthesized aspirin, one with commercial aspirin, and then one with salicylic acid solution, which I already have made up. The commercial aspirin and the synthesized aspirin you're going to dissolve up in ethyl acetate. You're going to set up a developing chamber with 60 to 40 hexanes ethyl acetate, which will already be pre-mixed. You're going to obtain a TLC plate, and then you're going to prepare that plate as I showed you previously. So you're going to put a pencil line across the bottom, 1 centimeter from the top. Right just above that line, you're going to put 3 spots. So one spot is going to be for your salicylic acid, one spot is going to be for for your synthesized aspirin, and one spot for your commercial aspirin. And then you're going to spot each sample separately, and you're going to develop that plate and calculate the RF. What you want to ask is here, right? What's the RF of the synthesized aspirin? How does it compare to salicylic acid? How does it compare to commercial aspirin? Which compound is more polar? You can tell that based on where the spot is on the plate relative to the others, and also by the RF factor. And then what functional groups are responsible for the polarity of the 3 compounds. Here I would suggest that you go back to last week's experiment and look at the structures for aspirin, for salicylic acid. So if you have any questions, just feel free to email me.